This is a recording of a lecture that was given on Wednesday, September 9th, regarding correlation and experimentation. The first section is on correlation. A correlational study is any sort of study that looks at the relationships between two different variables. So, say, for example, I wanted to explore the relationship between height and intelligence. Well, I could then measure everybody, all the participants in my study. I could measure their height. Obviously, just using a normal tape measure or anything else like that. And then I could give each of them an intelligence test. And based on that, I could see whether or not being taller makes you smarter or being shorter makes you smarter. Or if height has no relevance on intelligence at all, which it probably doesn't. Now, when we look at correlation, there are a lot of things in the world that are correlated, and a lot of times we experience it in our own life. For example, two things that are definitely correlated are the amount of calories you intake and how much weight you gain. If you take in more calories, you're going to gain more weight, at least for the most part. But sometimes we run into things that we think are connected, but actually aren't. These are referred to as illusory correlations. For example, when someone says that their joints hurt, and then they use that as a predictive measure for it being about to rain, or if someone says, come out of the rain because you're going to catch a cold, or maybe one of the most famous ones, the idea that parents think that sugar causes hyperactivity in children. None of these are true, and yet, based on our own experiences, we think that they are true. Just a little bit of side notes about that. The cold is a virus, and a virus can't be caused by water, but cold weather can weaken your immune system, which then makes you more susceptible to demonstrating a cold or demonstrating the symptoms of a cold. For the sugar and hyperactivity one, what they found is that when kids eat sugar, they're often around other kids, which makes them already a little bit crazier. But rather than attribute it to being around other kids, parents like to attribute it to the sugar itself. Sometimes kids are even told that sugar causes hyperactivity, and so therefore when they eat it, then they start getting more hyperactive. This is called a self-fulfilling prophecy, which we're going to talk about in a later unit. Ultimately, what we find is that sometimes things we experience in life aren't connected, even though we think that they are, and that's an illusory correlation. To demonstrate whether or not something actually is correlated, we have to look at the correlation coefficient. Correlation coefficient is a really, really complex statistical formula that will determine whether or not something actually is connected. If a correlation coefficient for something to actually be correlated must be between -1 and 1. If it's below -1, so like -1.5, or above +1, like +1.5, then we can say that there is no correlation at all. And that's often demonstrated by the graph that you see here with kind of the red line of X through it. Scatter plots, the graphing technique used to figure out whether or not something is correlated, is a statistical technique to show the relationship between two variables. If, for example, two variables impact each other, do correlate, and the increase in one variable causes the increase of another, like you see in the bottom right-hand corner, which is the number of, or the cost of donuts go up as the number of donuts you buy increases, then we can say that that is positive correlation. That's when both variables go up together or they both go down together too. A negative correlation isn't bad, and it doesn't mean that something isn't correlated. It just means that the relationship works a little bit differently. A negative correlation is when, as one variable goes up, the other goes down. The donut one here isn't the strongest graph, but as an example, let's say that you had a chart which is the amount of exercise you do, a scatter plot just like we see here, the amount of exercise that you do combined with your overall weight. Well, if you do very little exercise, your weight will probably be higher. And yet, as you increase the amount of minutes that you exercise, then the amount of weight that you have will in many cases go down. So we can see that that's a negative correlation. When the two variables don't impact one another, we can say that there is no correlation at all. And that's demonstrated by the graph in the top left corner. The closer a number is in its correlation coefficient, the closer a number is to either -1 or +1, the stronger the correlation is. So a correlation of 0.1 or -0.1 is not very strong, but a correlation of 0.9 or -0.9 is quite strong. A lot of times, though, when people see that there are two relationships between variables, they think it must be true. That must mean that this, in all cases, causes that. But one thing that we know for sure about correlation is that it does not equal causation. Correlation is the relationship between two variables. Causation is a proven logical cause and effect relationship. Let's say, for example, I was trying to do a study on the relationship between self-esteem and depression. Very common psychological study. We might find that those people who score higher on a depression scale test, meaning that they have higher levels of depression, might also self-report on a survey that says that they have low self-esteem. But does that mean that low self-esteem causes the depression? Or does that mean someone who's depressed will then inherently then have lower self-esteem? The problem is we don't know which one comes first if we just use a correlational study. To create causation, to create proof, we need to use an experiment. It could also be other factors, by the way, that cause the depression rather than just self-esteem as well. But we need to use an experiment to create causation. So how do we design an experiment? Well, that gets us to the next part. The first thing we need to do is we need to have a theory. A theory is just a question. It's an idea. But if that's all we have, it's really difficult to test in a logical step-by-step manner. So we need to go through these various steps to design our experiment, one that can create causation and one that can create a logical cause and effect proof. A theory is the idea. To turn a theory into a hypothesis, we need to demonstrate how we are going to measure it. How are we going to really look at this question? If we took that, I have an idea that low self-esteem causes depression, well, then our hypothesis could be those who have low self-esteem will score lower on a depression test. Now, this is a hypothesis because we can now use it and design our experiment around that hypothesis. Whenever we're creating a hypothesis, we also want to create a null hypothesis. A hypothesis, by the way, is just an alternative idea than what is out there before. A null hypothesis looks at the opposite of your actual hypothesis, and it's something that you try to disprove or nullify. Because even if you find that you don't have enough data to prove your hypothesis, if you have enough data to prove your null hypothesis wrong, then it's still just as good. So if we take a look at the picture on the slide here, we can see that an alternative hypothesis is something that we're trying to prove. Application of biofertilizer X is going to increase plant growth. Okay, that's measurement. So we're going to apply something and we're going to see an increase of plant growth, which we can then measure. The null hypothesis, which would be application of biofertilizer, does not increase the plant growth. Again, it's basically just the opposite to your hypothesis. Now, once we have our hypothesis, we also need to make sure that our experiment is capable of replication. Replication is really important because even if we prove something, there might have been some biases in there that we might not have identified before. So the operational definition is our specific way that we're going to measure this. Like, for example, if you're looking at the picture on the side, we might say that operationally, we're going to apply so much amount of this biofertilizer. And we're going to use a very specific tape measure, and we're going to measure in centimeters, not inches, for the amount of plant growth. This way, when another researcher goes to replicate your experiment, they can take a look at the operational definition and know exactly what to use and how to do it. Once we've got our hypothesis and our theories and we've defined our things, now we're going to start carrying out our experiment. In psychology, this means people. The population is anyone who is eligible for your experiment. This is generally a significantly large amount of people, and in some cases could be all the people on Earth or all the people in a country. From our population, the best way to create an unbiased results is to use random selection. What that means is that, let's say we've got 120,000 people in the city of Fairfield that we can choose from. We may randomly using maybe a computer or maybe voter registration or things like that. We may randomly select 1,000 out of that 120,000. This would be random selection. Let's not get random selection mixed up with random assignment, which we will get into in just a moment. Random selection is when you're choosing a number of people from your population and you do it in a random way. You do it in a way where it's not specific, I want to take you or I want to take you. It's, I'm just going to take a random group of people out of the larger pool that I can use. From there, I need to take my participants. These are the people who have been randomly selected. I take my participants and I split them into two groups. A control group is where nothing changes from the norm, where nothing changes from what's already been established. The experimental group is when something does change, is the participants that do experience the change. So if we take a look at the picture on the right here, we can see that in this experiment, will student test scores be affected by distracting sounds in the testing environment? The control group keeps it the same as it does. When there's a test, it should be quiet. So the control group takes the test while it's quiet, just to see what would happen normally. The experimental group, on the other hand, takes their test with lots of noise. And then we can obviously take those test scores and compare the results and see what effect that noise had on the overall student test scores. For a true experiment, we want to use random assignment. What that means is that out of our group that we've randomly selected from our population, all our overall participants, we want to randomly put those participants into either the control group or the experimental group. And we want to have the same amount of people in each group. But we don't want to choose it personally because that can create bias. What if we chose all the rich people in one group and all the poor people in another group, or all the men in one group and all the women in another group, or so on? What that does is it makes it so that that change may not cause the result. It could be the result of them being not kind of equal groups because they experience different aspects of life. So random assignment is when we take our participants and we randomly put them into either the control group or the experimental group. By doing it randomly, we can say that the difference in results comes almost entirely from the change itself. Finally, we need to look at our variables. In the control group and the experimental group, we have an independent variable. This independent variable will be different for the two groups. The control group, their independent variable is basically exactly the same. And in some cases, it's nothing. Or in some cases, in drug experimentation, it might be a placebo or a sugar pill. The independent variable is the change that is occurring from one group to another. So if we take a look at this experiment on the bottom, we could say that the control group is receiving no water because that's what they had before. And the experimental group is receiving amount of water, and that's the change that's occurring. The dependent variable is the measurement tool that we're going to use. In this case, on the picture that we see on the bottom, we could say that the dependent variable is the amount of seeds that sprout, and that's a way to measure it. If we look back to our previous slide, in this student test scores, we could say that the independent variable is the amount of noise that each group is experiencing, and the dependent variable is the student test scores. All of these are designed to show the effect of the independent variable. By using the same measurement tool, we can look at the differences in the results between the two groups and compare them to see if any change did occur. Now, we also know, though, that confounding variables play a role. These are additional things that might affect our experiment, especially in the case of people. So, for example, like socioeconomic class or gender or race could be a confounding variable that could affect how people experience the change in the experiment. Confounding variables obviously limit the effectiveness of an experiment because when there's differences in results, do we know whether it is from the change or whether it's from these other things, these confounding variables? One way of getting around this is by using random assignment. By randomly assigning participants into either the control group or the experimental group, what we find is that that eliminates a lot of the effects of confounding variables. Because if you have rich people in both groups and poor people in both groups, and men in both groups and women in both groups, and all sorts of other things, you have diversity in each group. And by doing that, if you have diversity in both groups, then we can say that the difference is not because of the differences in the participants, but instead just the change that they're experiencing. Finally, we want to take a look at something called a quasi-experiment. A quasi-experiment is like an experiment, but it's less perfect, would be the best way to put it. A quasi-experiment can come about if there is no control group. So say, for example, I give 8 kids M&Ms and I give 15 kids Skittles, and I want to measure the amount of hyperactivity that they're experiencing. Because I'm adding something new, because I'm changing something for both groups, that means that there's no control group. Now, I can still compare those results, and it's still fairly effective. But because there isn't a group that's receiving the control that receives nothing or no change, then it's not a true experiment. It's just a quasi-experiment. The other way that we can also create a quasi-experiment is by eliminating random assignment. If you lack diversity in the groups, obviously confounding variables will play a larger role, and that makes it not a true experiment. It makes it a quasi-experiment. So if, for example, one group, our control group, was men and our experimental group was women, we could still compare the results between men and women, but we wouldn't know if the results were due to the change or due to the differences in gender. Finally, 2 notes that I didn't include on here, but I will include in the actual lecture on Wednesday are single blind and double blind studies. A single blind study is when the participants don't know if they're in the control group or experimental group. So they don't know if they're receiving the change or not. This can eliminate bias from the participants who may act a certain way if they know what group that they're in. A double blind study is when both the researchers and the participants don't know which group is which, so therefore eliminating any potential bias that might occur when the experimenter might carry out behaviors that inadvertently affects the overall design of the experiment.